Our sun has sent out the strongest solar flare of 2025, and it sparked radio blackouts.
In the early hours of a calm day, a silent star unleashed a mighty burst of energy. In a flash, radio channels fell into eerie silence across many continents.
But scientists say that this is just the beginning and warn of more severe consequences as the sun emits.
Millions found themselves cut off from vital signals, bewildered by the sudden void. Questions echoed everywhere. What just happened to our sky? Why did the world go dark without warning? Today, we explore the event that stunned scientists and left nations in the dark. Just when we thought the sun's outburst was under control, a new contender, AR4087, was gearing up for a knockout blow. Stick around to find out how this warm-up act became the solar event that plunged half the world into darkness. The sun's surprise burst. In mid-May of 2025, our sun surprised everyone with a sudden series of eruptions. On May 13th, sunspot AR4086, the large dark patch on the sun's surface spotted within days earlier, unleashed an X1.2 class flare. This burst sent a pulse of X-rays and ultraviolet light racing toward Earth's atmosphere, briefly stirring the upper layers but causing only minor radio fade-outs in the Americas. By the next morning, activity had shifted to a new neighbor. That new region, labeled AR4087 by NOAA's Space Weather Prediction Center, began showing intense magnetic energy on May 14th. First came an M5.3 class flare just before dawn. M-class flares rank one step below the strongest X-class category, yet they still carry enough power to disrupt high-frequency radio at the poles and create minor radiation storms. This M-flare was a warning sign that AR4087 was about to roar. At exactly 4:25 a.m. Eastern Daylight Time, 08:25 GMT, on May 14th, AR4087 snapped its twisted magnetic fields with a massive X2.7 class flare. X-class represents the most powerful flares, each letter step meaning 10 times more energy than the one before. An X2.7 event is nearly 3 times more energetic than an X1.0 flare. The eruption unleashed a torrent of X-rays and extreme ultraviolet radiation traveling at light speed toward the sunlit side of Earth. Within seconds of the flare peaking, high-frequency radio waves began to vanish. Pilots, sailors, ham radio operators, and air traffic controllers found static or silence on vital channels. Europe, Asia, and the Middle East, those regions bathed in daylight at that moment, experienced what NOAA calls an R3 level blackout. R3 is classed as strong, capable of causing widespread shortwave radio disruptions lasting up to an hour. Alongside radio silence, instruments on board NOAA's GOES-19 satellite captured the flare's flash in multiple wavelengths. Images showed bright loops of plasma arching over AR4087 before snapping back like stretched rubber bands. These loops, filled with superheated gas at millions of degrees, marked the explosive release of pent-up magnetic stress. Though the initial X2.7 flare did not launch a coronal mass ejection, CME, directly at Earth, scientists remained on alert. CMEs are massive clouds of charged particles that can follow flares days later. If aimed at our planet, they can spark geomagnetic storms, endanger satellites, disrupt GPS signals, and even trigger power grid issues at high latitudes. Remarkably, just hours after the X2.7 blast, AR4087 produced yet another outburst, a further M7.7 class flare. This rapid sequence of strong flares signaled that the sunspot's magnetic fields were far from calming down. As AR4087 turned more toward Earth in its solar rotation, experts warned that the chance of more disruptive events was high. The timing of these flares fell near the peak of solar cycle 25, the sun's natural 11-year rhythm of rising and falling activity. Solar maximum, the cycle's most intense phase, arrived in late 2024 and extended into 2025, bringing more frequent and stronger eruptions. In this peak period, large sunspots like AR4087 become the main drivers of dramatic space weather. It was clear that May 14's flare represented the sun's growing restlessness during its solar maximum. Sunspot AR4487's surprising burst not only left a broad swath of Earth in radio darkness, but also set the stage for further shocks in the days to come. But what exactly makes these solar tantrums so powerful, so capable of blacking out half the planet in minutes? What invisible forces are unleashed when the sun lashes out with an X-class flare? To understand the true danger we're facing, we have to dissect the beast itself. Anatomy of an X-class flare. An X-class flare is the strongest category of solar flare. Scientists sort flares by how bright they appear in soft X-rays. The scale has 5 main groups: A, B, C, M, and X. Each letter is 10 times stronger than the one before. Within each group, a number from 1 to 9 shows the strength. So, an X2 is twice as strong as an X1 flare. These blasts release massive amounts of energy into space. Instruments on board NOAA's GOES satellites measure X-ray brightness in the 1.0 to 8.0 angstrom range. When the peak X-ray flux passes 10 to 4 watts per square meter, the event is classed X. A flare at X1.0 marks the threshold. Anything above is still X-class, with numbers going up to X99. This method is like the Richter scale for earthquakes, where each step represents a 10-fold increase in power. X-class flares form when magnetic field lines in the sun's atmosphere break and reconnect. This process, called magnetic reconnection, happens in active regions where magnetic fields twist and cross. When reconnection occurs, it converts stored magnetic energy into heat, light, and particle acceleration. The resulting explosion heats gas to tens of millions of degrees and sends high-energy particles speeding into space. Active regions appear as dark sunspots on the sun's surface. They are areas of intense magnetic fields. When these fields tangle, they build pressure beneath the solar surface. If the stress grows too great, the fields snap and realign in a sudden burst. This unleashes both a flare and often a coronal mass ejection. An X-class flare is a sign that the magnetic fields were extremely twisted. During an X-class flare, the sun emits radiation across the spectrum. The most noticeable burst is in soft X-rays and extreme ultraviolet. These wavelengths travel at the speed of light and reach Earth in just over 8 minutes. This flash ionizes the upper atmosphere, disrupting radio communications over the sunlit hemisphere. Particles accelerated by the flare can follow and trigger radiation storms lasting hours. X-class flares are rare compared to smaller events. During a solar maximum, they may occur around 10 times per year. In quieter times, they are far less common. Their occurrence rises and falls with the 11-year solar cycle. When the sun approaches its peak activity, active regions grow larger and more complex, making strong flares more likely. Even after the flare's light passes, its effects continue. The energized particles can flow outward in a coronal mass ejection. If aimed at Earth, a CME can drive geomagnetic storms, which may last days. These storms affect satellites, navigation, power grids, and even pipeline corrosion. An X-class flare without a CME still poses a short but intense radio blackout. The recent X2.7 flare from region AR4087 showed these features clearly. Its magnetic reconnection heated plasma to over 20 million degrees. The GOES-19 satellite recorded a peak X-ray flux more than twice the X1.0 level. Ground stations from Madrid to Mumbai reported loss of high-frequency signals. This flare showed how powerful and fast X-class events can be. Understanding X-class flares is important for space weather forecasting. Scientists use magnetic field maps and solar images to spot regions likely to flare. They monitor active regions for growing complexity and energy buildup. Advances in solar observatories and modeling help predict when reconnection may occur. This work aims to give early warning and reduce risks to technology and life on Earth. Radio blackouts. Explained. Solar radio blackouts begin when a powerful flare on the sun sends a burst of X-rays and ultraviolet light toward Earth. These high-energy rays reach our planet in just over 8 minutes. When they arrive, they slam into the lowest part of the ionosphere, known as the D layer. Under normal conditions, the D layer absorbs only a small amount of radio energy and lets most high-frequency signals pass through to higher layers. During a strong flare, however, electron density in the D layer jumps dramatically. This sudden surge turns the layer into a dense fog that soaks up high-frequency waves. As a result, shortwave communications between 3 and 30 MHz can disappear without warning across the sunlit hemisphere. To gauge blackout strength, scientists use a 5-level scale from R1 to R5. Levels correspond to peak X-ray measurements in the 1.0 to 8.0 angstrom band. An R1 event brings slight fading on some channels and lasts only a few minutes. An R2 blackout can cut off high-frequency radio for tens of minutes over a regional area. An R3, classified as strong, blocks HF signals across wide regions for up to an hour. R4 and R5 events cause even more severe and prolonged losses, sometimes lasting several hours and affecting navigation frequencies. This ranking helps operators know what to expect when a flare crosses each threshold. On May 14, 2025, at 08:25 GMT, sunspot AR4087 erupted with an X2.7 class flare that triggered an R3 blackout. Europe, Asia, and the Middle East fell under sudden high-frequency silence. In Spain and France, ham radio operators found their signals absorbed by the lower ionosphere and replaced by static. Over India and Pakistan, pilots on long-haul flights reported severe interference and switched to satellite links to maintain contact with air traffic control. Ships sailing in the Arabian Sea lost daily weather updates and navigational bulletins until the D layer's ionization subsided. Even emergency services in remote areas felt the impact, relying on backup communications to send alerts and coordinate responses. The blackout peaked within minutes and faded as the sun's X-ray output dropped, but the abrupt loss highlighted our dependence on shortwave radio. Mitigating radio blackouts relies on fast alerts and redundant systems. Agencies like NOAA issue real-time warnings based on satellite X-ray sensors. Tools such as D-region absorption prediction models produce maps showing where HF paths will fail and for how long. Operators watching these maps can reroute signals to higher bands above 30 MHz or switch to very high frequency and satellite channels. Modern radios often include automatic frequency hopping features that detect blackouts and shift bands without human input. In the aviation and maritime industries, crews carry satellite terminals for backup voice and data links. Emergency responders use a mix of cell networks, VHF radios, and satellite beacons to stay connected when HF goes dark. Lessons from past events drive improvements in forecasting, hardware design, and training, helping critical services maintain communication even during the sun's most violent outbursts. Behind the sunspot AR4087. Sunspot AR4087 emerged as a complex magnetic region on the sun's surface, quickly drawing the attention of solar scientists worldwide. Located at roughly 15 degrees north latitude and 30 degrees east longitude on the solar disk, this sunspot group displayed a rare beta-gamma-delta magnetic configuration, a sign of intense and unstable fields. In this arrangement, magnetic polarities are so tightly interwoven that they can store enormous energy, often leading to powerful flares when the fields realign. The origin of AR4087 traces back to giant magnetic flux tubes rising from deep within the sun's convection zone. As these twisted tubes broke through the photosphere, they formed visible dark spots surrounded by bright plages, areas of enhanced ultraviolet emission. Observations from NASA's Solar Dynamics Observatory, SDO, showed that the sunspot's umbra, or darkest core, spanned nearly 30,000 kilometers, large enough to stretch from New York to Los Angeles. Surrounding penumbral filaments extended the total area even further, marking AR 4087 as one of the largest active regions of solar cycle 25. Within days of its appearance, AR 4087's magnetic fields grew more complex. Spacecraft magnetometers measured rapid changes in field strength and polarity, indicating the buildup of magnetic shear and twist. These dynamics are driven by subsurface motions. The churning plasma beneath the photosphere forces the magnetic lines to tangle over time. When the stress becomes too great, the lines snap and reconnect in a process known as magnetic reconnection, releasing stored energy as heat, light, and particle acceleration. AR 4087's initial flaring activity began with moderate C-class bursts on May 10th and 11th. These smaller flares served as precursors, gently disturbing Earth's space environment without major impacts. As the region rotated closer to the Sun-Earth line, flares escalated in intensity. On May 13th, AR 4087 produced an M5.3 class event, foreshadowing greater eruptions. By the morning of May 14th, the sunspot had accumulated enough magnetic energy to unleash the X2.7 flare, its first X-class event of 2025. After the X2.7 eruptions, AR 4087 continued its volatile behavior. Less than 4 hours later, it launched an M7.7 class flare, showing how rapidly the region could re-energize its magnetic fields. This rapid-fire sequence is rare. Most active regions require days or weeks to rebuild after a major flare. The close timing suggests an especially intricate field structure, with multiple flux systems interacting beneath the surface. The sunspot's westward rotation toward the solar meridian brought its core directly into Earth's view. As AR 4087 faced our planet squarely, the risk of Earth-directed coronal mass ejections, CMEs, rose sharply. While the X2.7 flare did not immediately launch a CME toward Earth, coronagraph images showed loop structures lifting off, hinting that charged particles could follow days later. Scientists at NOAA's Space Weather Prediction Center warned that even a glancing CME impact could drive geomagnetic storms, affecting satellites and power grids at high latitudes. Researchers use AR 4087 as a case study in predicting extreme space weather. By combining high-resolution solar images, magnetograms, and computer simulations, they aim to map the magnetic topology and estimate flare likelihood. Advances in machine learning models now analyze thousands of sunspot parameters to flag regions with Delta-class configurations like AR 4087. This work strives to increase warning times from minutes to hours, giving operators more time to protect satellites, reroute flights, and safeguard power systems. As solar cycle 25 reaches its peak, sunspot AR 4087 shows the power of the sun, its growth from a small magnetic disturbance to the source of the strongest flare of 2025 illustrates how dynamic and unpredictable space weather can be. So, how do scientists turn a boiling mass of magnetic chaos, like AR 4087, into a forecast? And can we really outsmart the sun before it lashes out again? Solar maximum context. Around late 2024 and throughout 2025, Earth will move into the peak phase of solar cycle 25, known as solar maximum. This cycle began in December 2019, marking the start of an 11-year rise in sunspot numbers and solar activity. During solar maximum, the sun produces more sunspots, solar flares, and coronal mass ejections than at quieter times. Scientists watch this period closely because intense events can affect technology and life on Earth. At solar maximum, sunspot totals reach their highest levels. Projections made by the International Solar Cycle Prediction Panel estimate a peak of about 115 sunspots in July 2025. This count places cycle 25 as moderate compared with past cycles. For example, solar cycle 24 peaked at 116 sunspots in April 2014, while cycle 23 reached over 180 in 2000. A moderate peak still brings frequent solar storms and bright auroras, but poses fewer extreme risks than a stronger cycle. Sunspot numbers are tracked using a smoothed monthly average. This method filters short-term rises and falls to reveal the cycle's long-term trend, as the smoothed sunspot number climbs toward its maximum. Solar observatories around the world record growing numbers of active regions. By early 2025, sunspot counts had risen each month, signaling that the Sun was entering its most energetic phase in the current cycle. A key feature of solar maximum is the surge in X-class and M-class flares. During quieter phases like solar minimum, these large flares are rare. In contrast, dozens of strong flares can be seen in the above-average years at the top of a cycle. In the months leading up to May 14, 2025, scientists recorded multiple M-class flares and a few smaller X-class events before the record X2.7 flare from AR4087. These bursts of energy show how sunspot complexity and magnetic stress build as maximum approaches. CMEs also become more common and energetic during solar maximum. CMEs are huge clouds of electrified particles that can follow flares into space. If aimed at Earth, they can drive geomagnetic storms that disturb satellites, GPS, power grids, and high-latitude radio links. Between late 2024 and mid-2025, a series of CMEs grazed or struck Earth's magnetosphere, causing auroras as far south as Texas and logging G-level storms on the NOAA scale. The effects of solar maximum extend beyond shortwave blackouts and auroras. Satellite operators track increased radiation levels that can degrade solar panels and damage electronics. Airline crews flying polar routes face higher radiation exposure and may need to change flight paths. Power companies in northern regions monitor geomagnetically induced currents in pipelines and high-voltage lines, which can overload transformers and trigger voltage dips or outages. Researchers also debate longer-term solar trends that overlay the 11-year cycle. One theory, the centennial Gleisberg cycle, suggests an 80 to 100-year rhythm of solar intensity. Recent data hint that we may be midway through a stronger multi-decade phase of activity, which could sustain elevated flare and storm rates beyond the current cycle's end. Confirming this pattern requires more years of observation. Solar maximum brings wide chances to study the Sun up close. NASA's Parker Solar Probe and the ESA/NASA Solar Orbiter, both launched when Cycle 25 was young, now sample the Sun's outer atmosphere and solar wind in unprecedented detail. These missions aim to reveal how the Sun's magnetic field evolves, how flares and CMEs originate, and how they accelerate particles that travel across the solar system. In addition to spacecraft, ground-based networks of solar telescopes and radio arrays monitor changing conditions on the Sun's surface. Instruments like the Daniel K. Inouye Solar Telescope capture high-resolution views of rising magnetic flux and small flares. Radio observatories track bursts of solar radio noise, signaling particle acceleration. This global effort helps forecasters predict space weather more accurately and issue timely alerts. Space weather forecasting has matured alongside the increasing risks of solar maximum. Agencies now provide real-time data feeds, forecasts, and warnings for flares, CMEs, and geomagnetic storms. Commercial services offer tailored alerts for airlines, power utilities, and satellite firms. As we progress through 2025's peak activity, these forecasts become important tools for minimizing disruptions and keeping people, infrastructure, and technology safe. Looking ahead, the Sun will gradually slow after mid-2025, entering the declining phase of Cycle 25. Sunspot numbers and flare rates will drop over several years until the next solar minimum arrives around 2030. Lessons learned during this maximum, from improved tracking of AR4087 to real-time blackout modeling will carry into the next cycle, strengthening our readiness for whatever the sun unleashes next. Global impacts and infrastructure. When the sun unleashed its strongest flare of 2025, the effects reached far beyond the glare of space. The technologies we depend on felt sudden strain. Satellites, power networks, transport systems, and communication links all faced unexpected challenges. This single flare tested how well our global infrastructure can stand up under extreme solar weather, and it highlighted the need for strong backup plans to keep services running when the sun turns stormy. Satellites in low Earth orbit felt the first toll. The burst of X-rays and ultraviolet rays heated Earth's upper atmosphere, causing it to expand. Denser air increased drag on satellites, slowing their paths and pushing them into lower orbits. To stay safe, operators powered down non-essential systems and fired thrusters more often, using extra fuel and shortening mission lives. At the same time, high-energy particles from the flare penetrated spacecraft shielding, risking damage to onboard electronics and solar panels. Down on the ground, power grids faced a different threat. When charged particles that followed the flare collided with Earth's magnetic field, they drove currents through long metal conductors, such as transmission lines and pipelines. These geomagnetically induced currents can overload transformers, cause voltage swings, and even trip protective breakers. Utility companies in northern regions monitor solar activity and may adjust grid flows or disconnect vulnerable equipment. Still, a strong storm can trigger rolling blackouts and costly repairs. Airlines also felt the flare's impact. On polar and oceanic routes, crews rely on high-frequency radio when VHF or satellite links are out of reach. During the blackout, radio operators heard static or lost contact, forcing pilots to switch to satellite voice systems or reroute flights toward lower latitudes. Radiation levels at high altitudes rose too, so some airlines altered flight paths and altitudes to protect crew and passengers. These changes cost extra fuel and time, but kept everyone safe under stormy space weather conditions. Maritime vessels depend on high-frequency bands for long-distance communication and weather updates. When HF channels went silent, ship captains switched to satellite phones and relied more on GPS and radar. Although GPS signals usually weather the initial flare, later geomagnetic storms can degrade accuracy. In the days after the event, some shipping companies chose routes with stronger signal coverage or delayed departures to avoid navigational risks on the open sea. Long pipelines and rail tracks can act like antennas during geomagnetic storms, picking up induced currents that accelerate corrosion and disrupt signaling systems. Pipeline operators install grounding systems and monitors to bleed off excess current safely. But strong storms may still force temporary shutdowns of pumping facilities. Rail networks may pause electric train services or switch to backup signals to prevent hazards on the tracks until conditions return to normal. Internet and telecommunications sit on a mix of fiber optic cables, undersea links, and cell towers. These systems are largely immune to direct geomagnetic currents, but they depend on stable power. Cell sites and data centers run on backup generators and batteries during outages, yet prolonged grid failures can slow or halt internet exchanges. Remote areas with limited backup may experience short service drops until power is restored, highlighting the digital divide when storms strike. The economic cost of a major solar flare can soar into the billions. Fixing transformers, replacing satellite parts, and covering airline diversions add up fast. Insurance firms now offer space weather policies, though claims can be complex when damage is indirect. Governments and industries run drills and risk assessments to estimate potential losses and refine emergency plans. These exercises aim to limit economic fallout and speed recovery when the sun next decides to roar. Building resilience depends on accurate space weather monitoring, fast alerts, and robust system design. Agencies share real-time data from satellites and ground sensors, giving operators hours of lead time to switch systems into safe modes. Critical infrastructure includes automatic shutdown and rerouting procedures, hardened materials to withstand currents, and backup communications for crews at sea and in the air. As Solar Cycle 25 winds down, lessons from this flare will guide preparations for future storms and help protect our interconnected world. Monitoring and outcomes. But when the sun strikes, who answers first? And how fast? With billions at stake and minutes on the clock, response teams must act with surgical precision. So, what does a global reaction to a solar superflare actually look like in motion? After the X2.7 flare from sunspot AR4087 burst toward Earth on May 14, 2025, space weather teams raced to monitor its effects and guide responses. Within seconds, satellites streamed data on the flare's ultraviolet and X-ray output, revealing its intensity and timing. Ground-based instruments simultaneously tracked disturbances in the ionosphere and magnetic field. Real-time coordination between satellite controllers, forecasters, and infrastructure operators proved critical to limit damage and guide recovery efforts. In the hours and days that followed, a sequence of alerts, surveys, analyses, and public updates laid the groundwork for stronger resilience against future solar storms. Satellite operators acted first. As the flare's extreme ultraviolet light heated the upper atmosphere, low-orbit spacecraft faced increased drag and shifting orbits. Controllers placed vulnerable satellites into safe mode, shutting down non-essential systems and boosting thrusters to maintain altitude. Radiation sensors on board flagged elevated particle levels, prompting teams to power down sensitive electronics. Weather and communication satellites extended their eclipse avoidance maneuvers. By prioritizing core systems and delaying routine operations, mission teams minimized hardware wear and preserved fuel that would otherwise be spent correcting flare-induced orbital decay. Meanwhile, the Space Weather Prediction Center issued rapid alerts. Automated X-ray flux measurements triggered an R3 blackout warning, shared via web dashboards, text messages, and email feeds. Subscribers included airlines, shipping companies, power utilities, and emergency services. Airlines rerouted polar flights to avoid communication gaps and higher radiation at altitude. Ships are prepared to navigate by radar and GPS in case high-frequency links remain down. Power grid managers began adjusting transformer loads and activating protective resistors to limit geomagnetically induced currents. These preemptive steps helped prevent service interruptions and equipment damage as the flare's charged particles reached Earth. Across Europe, Asia, and the Middle East, ground sensors logged the flare's impact on the ionosphere and geomagnetic field. Ionosondes recorded a sudden surge in electron density in the lower ionosphere's D layer, causing shortwave radio channels to fade for nearly an hour. Magnetometers then detected shifts in Earth's magnetic field as the flare's coronal mass ejection arrived, driving currents through long conductors like power lines and pipelines. By mapping these changes in real time, forecasters refined their predictions of blackout duration and geomagnetic storm strength, allowing operators to adjust response plans on the fly. The day after the event, engineering teams conducted systematic surveys of critical infrastructure. Utility crews in northern regions inspected high-voltage transformers for overheating and voltage irregularities. Pipeline operators reviewed corrosion monitors to ensure no unexpected currents had stressed buried metal lines. Telecommunications providers tested undersea cable repeaters, confirming that backup generators and battery systems functioned correctly. Internet exchange points verified that their uninterruptible power supplies could sustain operations through longer outages. By identifying and correcting minor faults early, these teams forestalled more serious failures and shortened recovery time. Scientific analysts then dove into detailed evaluations of the flare and its effects. Researchers compared live data streams with forecasts generated by machine learning models trained on past solar events. Where predictions diverged from observations, modelers adjusted algorithms to improve future accuracy. Solar physicists used high-resolution magnetograms to reconstruct the magnetic reconnection process within AR4087, tracing how twisted fields snapped and released energy. Ionospheric scientists fed real-time absorption data into their D-layer models, fine-tuning estimates of radio blackout onset and recovery. This feedback loop between observations and models strengthened forecasting tools across multiple disciplines. Public communication teams worked in parallel to keep communities informed and prepared. Space weather centers published plain language summaries explaining the cause of radio blackouts, the reasons for flight diversions, and the potential for auroras at lower latitudes. News outlets carried advice for amateur radio operators and remote areas relying on shortwave. Social media posts encouraged individuals and businesses to test backup power systems and review emergency communication plans. By demystifying complex solar physics and providing clear action steps, communicators built public trust and promoted safety during future space weather events. Envisioning lessons from the AR4087 flare are guiding upgrades to monitoring and response systems. New small satellites are slated to fill observational gaps, offering higher cadence imaging and expanded X-ray coverage. Ground-based sensor networks will extend into polar and oceanic regions, where data remains sparse. International agreements are strengthening real-time data sharing to speed alerts across borders. Utility, aviation, and maritime sectors are embedding space weather feeds into their operations centers, enabling automated adjustments when warnings arrive. By weaving resilience into system design and procedures, these measures aim to keep our global infrastructure safe, effective, and ready for the Sun's next challenge. Thank you for joining us as we explored the Sun's mighty X2.7 flare and its global blackout effects. Please share your thoughts in the comments and make sure you do not miss our next video.